Good morning from Virginia. My name is Barbara Dill, and I'm happy to present a demonstration that shows how to use the conceptual model of multi-axis spindles. In this demonstration, I will be presenting one or two projects, and I'll start from the beginning, how to plan it, how to use all the concepts we've heard about, the families, the quadrants, the variables, to plan a project, make it your own, and how to turn it. So first, because you may not have seen the first demonstration, I will have a brief overview of that conceptual model. I hope you enjoy this. Well, I just showed a short video of my shop because it is February in Virginia and it is snowing, and I do have a fire in my wood stove, so you may hear it crackling in the background. But now we're just going to go over the basics of this conceptual model. What do all these spindles have in common? They must have something so that we can understand them. Well, they do. There are only two ways that the new axis can be moved relative to that center axis. That new axis will either be parallel to that center axis or not parallel, which we call twisted. And there are only two results or outcomes that happen when you change an axis: arc type and circular type. So I'm going to unpack these ideas slowly. About the axis placement, the pictures in the upper left-hand corner are the two basic ways that the axis will be changed relative to that red center axis. It's either going to be parallel, meaning the same distance and direction from the center axis, or not parallel, which is twisted across that axis or any line parallel to that center axis. The rest of these are just ideas about all the millions of ways the new axis can be placed. And there are only two results that can happen when the axis is moved from the center axis to a new axis: arc type and circular type. Now, how does that happen? So, arc type happens when you only cut into the air wood, or the wood that's not between the headstock and the tailstock. So let me explain. This spindle has a center axis. It's probably right where my arrow is. I now put it on a parallel axis closer to the outside of the spindle. The new solid wood is here, and as it turns, this is going to look blurry. It's called ghost wood or air wood. And when you're creating an arc type spindle, then you're cutting into that air wood. Here are some examples of arc type, and there are actually two types of arc types. There's parallel. This is the one on the left, and these are parallel axes to that center axis. On one axis, let's say it's where my arrow is and it's parallel to that center axis. Then I turned a bead and a cove and a bead. And then in the same plane as the center axis and 180 degrees from that first axis, there's a second axis on which you turn then a cove under the bead, a bead on top of that cove, and a cove under that bead. So that's an example of parallel arc type. This walnut one is an example of twisted arc type. In this case, there are three axes separated by 120 degrees with a long cove turned on each axis. So here's just what, if you dissected them or cut them in half, you would see these profiles intersecting and they look like arcs or lenses, so they're called arc type. And then for circular type, you go all the way through that air wood and grab the solid wood that's between the headstock and the tailstock, and on that solid wood you can turn a profile. So here's some examples of circular types. They also have two types, twisted and parallel. The twisted one is on the left. It has one axis on the top and probably four on the bottom. And on every axis you went to the solid wood, just created a cylinder and did that again and again and again. And you can do that same idea on parallel axes. But the essence is that you've grabbed that solid wood. So if you cut these in half, you would see a cylinder. You would see a circle. Now let's take a look at where the axis should be placed. On circular type, if you put the axis closer to the outside of the spindle, The radius defines the size of the new cylinder. So in this case, there wouldn't be a very large cylinder on which to create profile, and it might not even connect on circular types. But if you put the new axis closer to the inside or center of the spindle, then therefore the radius, once again, is defined by the distance from the outside, from the axis to the outside of the spindle, and then the solid wood is going to be a lot larger, and you'll probably have a lot more success turning a circular element on that. With arc type, it really isn't that critical, because if the new axis is placed closer to the outside of the spindle, the radius will be longer and the arc will be flatter. And if the new axis is placed closer to the inside of the spindle, the radius will be shorter and the curve will be more curved. So it's not that critical for arc type. So there are a couple of axes that you show how that works. So now we have identified 4 major components of multi-axis spindles. We've defined axis placement, which can be parallel and twisted, and we've defined outcomes, which can be arc type and circular type. So now we have a table, and this table has 4 quadrants, and it represents 4 families of spindles that have things in common. They have axis placement and type in common. So in quadrant 1, all those spindles or parts of those spindles will have arc type and parallel axes. In quadrant 2, all those spindles will have arc type and twisted axes. Quadrant 3, all of those spindles will be circular type with parallel axes. And quadrant 4, all of them will be circular type with twisted axes. So let's look at how that works. So on top of that line, those 2 quadrants, quadrants 1 and 3, are going to have parallel axes, but one will be arc type and one will be circular type. And below it, all those 2 quadrants will all have twisted axes. One will be arc type and one will be circular type. And once again, on the left-hand side, those 2 quadrants are all arc type, and the circular type are going to be on the right. So there is a handout that you can get off of my website that shows the essence of this model and how it works. You can also combine ideas, and on one spindle, let's take the one in the middle, the walnut one. On the top, there are 3 axes separated by 120 degrees. On the top, it's parallel arc type. On the bottom, it's twisted arc type. And in the middle, it's circular twisted because it's on an off axis. Now let's discuss the variables briefly. Because I was a nurse, I call this the anatomy of a spindle. So this spindle has a piece of wood, the size and shape of the wood, a profile, and an axis. Under those 3 categories are most of the variables, and these variables apply to each quadrant. Let's take the basics of the profile. The profile, I just break it down into beads, coves, angular cuts, V-cuts, straight lines. Now, these elements can be symmetrical or asymmetrical. They can be short or long. They can be deeply cut or not so deeply cut. So there's a lot of variation just with those simple elements. The size and the shape of the wood makes a huge difference. When you turn an idea on a long, slender piece, you might get an outcome that looks like that. And then if you turn that same piece in a square piece of wood, like a 6-inch square, you turn it exactly the same way and you get an object like that. So size and shape of the wood can make a huge difference on the same idea that you want to turn. And when you look at axis placement, you've seen this slide before. These ones on the top show the basic types of axis placement, either parallel or twisted. But then let's look at this spindle that has 1 axis on the top and 2 on the bottom. This one has 2 parallel axes to each other, but they're twisted relative to the center axis. That's the way that harmony piece was in the last slide. Here's a drawing that you can hardly see. There are 3 axes separated by 120 degrees, and they're parallel axes. Here's that same drawing but they're twisted axes. 3 axes separated by 120 degrees and twisted. Here's 4 axes separated by 90 degrees. The axes don't have to be separated by equal amounts of space. They can be randomly placed anywhere, and they can even be placed on the side of the wood. And now for another really important thing, it's because you have to have a systematic way to think about this so you don't get a brain cramp. So this is my systematic way of numbering. The bottom is always the headstock. The top is always the tailstock. I would draw it that way, but it's confusing to me, so I don't. So I number everything. Let's say there are 3 axes separated by 120 degrees. I number them 1 to 1, 2 to 2, and 3 to 3. So parallel axes, that's pretty easy because you turn 1 to 1, 2 to 2, and 3 to 3. But what if they're twisted? So I would go 1 to 2. I'd number them the same way, but I would always start at the headstock end with the lowest number and go to the tailstock end with the next highest number in sequence. So it would be 1 to 2, 2 to 3, and then in sequence 3 to 1. If I do that all the time, then it's a lot less easy to be confused, but there is confusion in all of this type of turning. The drawing on the left just shows 4 quadrants, how you can turn a 90-degree twist instead of a 120-degree twist, 1 to 2, and then behind it 3 to 4 if you just want to do 2 axes. This image here just shows that when I turn a spindle, I like to draw a line on each end, and that's where I mark these numbers, because it's really easy if you're having all the points on the ends and it's hard to read the ends, and it's easier and less confusing to see where the axes are if you put them on the outside of the spindle. Also, this section I'm going to show you how you use all of that information that we've just covered. Those variables, the families of spindles, all the different ways you can create different objects using those ideas. So the first project is going to be a 3-sided cup, and then next I'll do a twisted circular candle holder. So let's take this long spindle over here, that walnut spindle that has 3 axes that's divided by 120 degrees and twisted at 120 degrees. We're going to shrink it into some wood that's fatter and not quite as long. These have the same idea as that walnut spindle. There are 3 axes separated by 120 degrees and also twisted at 120 degrees. Notice that the twist goes in different directions. The only way I can manage that is to number them differently. I can't do the math in my head, numbering them in the same direction and then doing it that way, but that's just me. Here's some different cups, different sizes. So the twists are different. You don't have to twist 120 degrees. But look at the various sizes and shapes you can get depending on the size and the shape of the wood that you use. So first you have to decide on a piece of wood, and you have to decide the dimensions of that wood. So this project has a piece of walnut that's 5.5 inches long and 4.5 inches wide. The first thing to do is to turn it into a cylinder. I create a tenon on each end. The tenons are not for 4-jaw chucks. The tenons are going to help me see how deep to cut on each axis on each end. I didn't start doing that. I started not using tenons, and I would draw a circle on the end, so that meant I had to continually look at the ends to see how my depth of cut was. And the second problem was, and I'll show it in the next slide, the second problem was that if I didn't have a tenon, these points that the headstock and the tailstock made in the wood would have to be turned off. So if I thought that goblet was going to be this long, I would have to take off some wood on the top and the bottom. So I developed this idea of getting a tenon involved. It helps me find the depth of cut, and then I remove it when I start hollowing the cup out. That's a indexing jig, and it helps find angles. There are many ways to find the angles. That's one of many ways. And so here is a better explanation of that tenon. The tenon on the top represents the lip, the outside lip of the cup, and on the bottom it represents the bottom of the cup. So normally the top is going to be a little smaller, the bottom tenon is going to be a little larger, but both tenons need to give you enough room between the outside of the outside of the spindle and the tenon to be able to have the axes intersect and touch that tenon. So here's just a drawing. You'll see axis 1, I put the lathe there. I'm cutting off in the air wood that arc. I'm touching that tenon. Then I go to axis 2, which is the green axis, and I do the same thing, cut an arc and touch that tenon, and then do the same thing on the third axis. It just makes it a whole lot easier in order to be able to turn these and make the axes the same depth of cut. Now, this just shows you that sometimes I'll go ahead and push a point in each end because it's hard when you're at an angle to get that point in exactly the right place, and accuracy is really important. So now here's what it looks like on that first axis. It's on 1 to 2. It could be on 2 to 3 or 3 to 1. Doesn't matter where you start as long as you go in sequence. Here are a few things I wanted to mention before I start showing you the video. And here I'm pressing the points in each end of the wood. It's probably not that important on a thick piece of wood like this, but I get in the habit of doing it because on a thinner piece of wood, you have to press all these points in before you thin it out and make it fragile. See me use for this is the 1/2 inch bowl gouge sharpened like a spindle roughing gouge. I've become quite fond of that tool. I have a good control of it. It can reach over the tool rest very nicely. And my tool of choice is always the one that I can make the smoothest cut with. Sometimes it is a spindle gouge. In this case, it will probably be the 1/2 inch bowl gouge. Another issue you might wonder as you see this progress is how to visualize the same curve on each axis. And that's why I mark the ends with depth of cuts for me so I can at least get the same depth of cut on the top and the bottom on each axis. And then you'll see me measure the depth of the cove that I will cut, and I'll mark it on the tool rest so that, and the tool rest will never move because I don't need to move it. All the axes are the same distance from the center axis. So I can use the tool rest as a reference point, and I'll know the depth of cut then on the bottom where the cove is and on the top. And then it's just by repetition and visualization that you can match the curve on each axis. It just gets easier over time. Now what you're going to see in this video is how it looks when it's turning. So what I'm doing here is I'm going to kiss the tenon on each side. Those are my initial cuts in order to create this cup. Nice gentle cuts. Lighting is important. I stop and start a lot just to find out where I am. So far I have a little to go here and on each end. So I will keep cutting. Once I find that depth of cut, tighten this up a little. Then I'll create the profile. Now I'm starting to eat away at that profile. I'm going to have a cove down at the bottom so your hand can go around this step. And then it's going to have a nice bead at the top. So I've kissed that, and now I've started the cove, and I need to make a nice gentle curved bead that curves into that top. So it's developing. Well, I have refined that cut just a little more. And now what I'm going to do, I'm not going to move the tool rest on all three axes because the axes are equidistant from the center axis. So I can use it as a reference point, and I can make a mark on it indicating the place on this cup that the deepest part of the cove is, and I can measure it off of the tool rest so it's that far off. So I'll save that measurement, and now I'll change it to the next axis. This was 2 to 3. Then I'll go 3 to 1 in my sequence so I don't get confused. So now it's on the second axis, which is 3 to 1 in sequence. Once again, I will cut on each end to find the depth of the cut. I will kiss that tenon because it's there as a reference point. It saves me from having to look around on the very end if I had drawn a circle on the end, which is what I used to do before I realized these tenons could be used as depth indicators. Stop the lathe. There, I still have a little to go there and a little to go there. Better stop it prematurely than take too much out. Although if you take too much out, then what you have to do is do that on all the axes. And then at the very end, sandpaper is your friend if you need to sand down some things to make everything equal. Well, I think I've got them about equal, and now I'm going to take off some of this wood, focus down here on a cove. I turn the speed up a little bit. Makes it a lot easier to make a smoother cut. Before I turn the lathe off, I'll probably take some more wood out and just try to make a profile that looks good to my eye. And then I'll stop now and take some measurements. This has now kissed that and that, so that's good. And now the depth of cut, oh, it's good. It's a little deeper than the first one, but that's okay. So now I just want to make a few more cuts. No, I think I like it, and see how the axes are intersecting together nicely. So now I'll put it on the third axis. Okay, now I've got it on 1 to 2, and I can visually check it and see that that's where my tool will hit. But if I were going to be confused, I could always turn it on slowly, take a piece of chalk and just make sure that's the axis I want to be cutting. So I'll tighten it up a little more. And now do the very same thing. Find the depth of cut on each end. I've sped this segment up because it's the same as the first two axes. This is the magic of technology. Okay, so that looks good. That looks good. I'll measure the depth. And it's not quite as deep as the other two. And then I want to see, oh, there's a gap there. I don't know if you can see that. That's done nicely. These two intersect well, but I think I have to take a little bit more wood out of the axis that I'm working on right there. That intersection's good, that one's good. That one has a little gap on it, but if I could go deeper here, I'll keep trying to cut this away. There's a flat spot there, and it may be on that other axis as well, but okay, that looks good to me. So now all three axes have been turned. Okay, now it's back on the center axis, and what I'm going to do is make the tenon on this end the right size for my 4-jaw chuck, and then I will take the tenon off this end and make a cut that curves concave into the center, which will make the 3 points proud, more higher than the other part. You'll see. Need to make the tool rest a little closer. I can turn the speed up a little. Okay, that's pretty good. I'll take a little more off. And now I'll take my spindle gouge and I'm going to cut I'm going to cut the tips and go downhill, which will make them look like they're curving in to the bottom. That's just a design element that I like. And now on the top, we'll do the same thing. First, I will take the tenon off, and then I'll make a cut that goes downhill. Okay, now we'll just take the tenon off of the top of the clip. I'm going to use a smaller parting tool that has an angle on the point and capture the points Now the points are proud and you have a nice curve there. I used to do that with my spindle gouge, but I was younger then and I was successful with it. Now I'm usually not successful with using this tool to do that. Now it's a matter of putting it on the 4-jaw chuck and hollowing it. Now I like to use a drill bit to make hollowing a bit easier, so I'll use my tail center with a drill bit in it so I can hollow out easier. And I use calipers to find the depth, the thickness all the way down. So I take the thinnest part and use the calipers down that thinnest part, not where the axes come together, but the thinnest part. And the hollowing tools I use vary. Sometimes I can use a scraper. There's another scraper. This is McNaughton's hollowing tool that I like. I have so many hollowing tools that some of them work on some days and some of them don't. So it's just a matter of choice. Once I've hollowed it, I have made a finger out of a dowel with foam around it and duct tape and then Velcro on it. And I can stick this finger in there and I can sand it a lot better than I can with my own finger. I've learned. So here is the final product of that walnut cup that we turned. It did have some really nice elements in it that I was able to fill with turquoise. These are great products. This is not a signature piece. It's free for anybody to make. They're a wonderful gift. Just add that these candle holders are essentially made the very same way that cup was made. It's a different form. The wood is longer. The twist is not 120 degrees. This next project is a twisted circular candle holder. As a review, here is an image of a lot of coves that are arc type. The cups are circular type. Well, what we're going to do is make circular type coves on larger pieces of wood. These are just some examples of the cups. This has 3 pieces of wood in it. That's from 1 piece of wood. Here's some of the candle holders I've made by using whatever number of axes that I want and then creating these candle holders. So I usually, for candle holders, will drill a hole in both ends before I turn them, just because they might get fragile and it's hard to put the pressure on the wood after they turn in order to put the holes in. I'll drill a hole 1 inch or 2 in so I can fill it with lead shot to weight down that candle holder so it's more stable on a table. So here's one example, and just notice on this side that I usually leave a piece of square wood here for the tool rest to hold it, so I don't have to hold it with my hand, because the torque is really difficult to hold as I drill in the holes on each piece. But there are many ways to do this. This project really didn't need a tenon, but sometimes I go ahead and do it just out of the routine that I get into when I turn. Of course, here are the ways that I can figure out what axes I want, and I think on the project that I'm doing this time, there are 5 axes on the bottom. And I've already pre-pressed in the points on this end, on the bottom, which is the headstock end, because that joint is really important. That's in grain, it's usually greenish wood, so you want to press it in, and that joint drives this whole turning. On the top, I use the cone center for my tailstock to put in that hole that I drill, so we have 1 axis on the top and 5 on the bottom. And just notice there are all these decisions that have to be made: how long the wood is, how fat it is, how many axes you want to use, how long the coves should be, how short they should be, the depth of cut, and on and on. So there's so many ways to change what I'm going to do to make it different. Anyhow, here we go. Okay, I've set this up now so that I have 5 axes marked on the headstock end, which will be the base. And I'm going to start cutting a cove, but I've made a mark in chalk the depth of the hole that I drill for the lead shot at the end. I don't want to intersect with that. I don't want that hole to interfere with the cuts I'm making. So now I'm going to turn a cove, and I'm going to make it circular, meaning I'm going to go through all of that air wood and get to the solid wood and make this cove. The tool I'm using is a tool that I like to use when I have to reach over the tool rest. I could use a spindle gouge, and this is a bowl gouge that's sharpened at the same angles on the Wolverine, just like the spindle gouge. It just is a heavier tool, so when I have to cut off the tool rest, it makes it a lot more secure. So I'm just going to nibble away at this wood. I've got a long way to go. always going downhill. I left room at the base for the weight. There are three things to notice on this video. One is when I widen that cove, I'm doing it on the right-hand side. I don't want to go any deeper on the left-hand side. Notice how far the tool is off the lathe, and also notice that because there's a lot of air wood, this is an interrupted cut, so the tool has to be held quite steadily. Trying to make nice light cuts. If they get really heavy, then I want to make them a little lighter. I'm not quite to the solid wood yet. But I'm getting there. Now I have cut deeply enough through the air wood to grab the solid wood, and now I'm going to refine this cut. That's easier to deal with now than use sandpaper later. And I might want to make this wider, meaning cut up here a little more just to open it up a little bit. So first let me clean this part up. I can find it this way. Oops, I lost it. As the diameter decreases, the tool handle gets lifted up. Then I'll widen this one up a little bit. And then smooth out that bottom of the cut. And see how it looks. It's a little ridge there I can get rid of now, but I'm satisfied with most of that cut. That's where it was bouncy a little bit because the bevel was touching the wood a bit too much there. And notice how far over the tool rest the tool is in order to reach the solid wood. And now that's pretty good. Now I'll move on to the next axis. I'm going to sand this. I'm going to sand it on each axis. I try not to go back to the axes, although it's possible to do that. So I want to get the tool rest out of the way and then keep my hand on this side and just touch that gently. Tool rest is rattling. But that's the way you sand circular type outcomes while you're on that axis. And then I can do that with a disc because I can't really sand that effectively right now as it's spinning. Now my next cut on the second axis is going to be right here. So I'll start right about here, but as you can see, the cut will go this way, and I'll have all of this wood to remove if I want a crisp edge. So I'll start here, and then I'll back the cut up so I can eventually capture this edge as well. Because time is limited, I am going to speed up certain sections of this. It takes me a long time to turn these things because I stop and start a lot. So you can see I've captured this edge and I'm going that way, so I'm going to have to back this cut up in order to get to that spot. I've stopped the lathe now just to see where that cut is relative to the flat areas that I need to remove. I've just about gotten a crisp line on that disc, so I need to back this cut a little more, make maybe a little deeper there. Ooh, still a little bit of a flat spot there. So I'll keep on working on that. And the diameter is a little fatter than this one, so I'll keep working on that before I move on. Okay, I'm happy with that. It's a crisp intersection of these two axes. I will grab my sandpaper, which is I think 120. It's cloth backed. It's easy for me to hold on to it. Keep my hand on this side of the tool rest. Of the lathe. I've moved the tool rest and give that a quick sand. Then I can move on. Here's the beginning of the third axis. My first cut will go here. I'll start making the cove here and then I'll back it up so I can grab the edge of the second axis. In addition to watching the way the wood is cut, notice that on the headstock end, where the axes are closer to the outside of the spindle, there's a lot more air wood and a lot less solid wood. And as we go up to the tailstock end, where the center axis is used, you can see that the air wood is less and less and the solid wood is more and more, meaning you just have to cut through a lot more solid wood to make that cove the same diameter as it is in the other elements. Now it's time to change the axis, and because I have a sequence, I'll know which number to go to next. So now I've done 5, and that's the way it looks. So much fun to watch it as it turns. And now I have to decide what to do up here at the top. Do I have enough room for another cove? No, I don't think so. So I'll focus on putting it on the first axis and then creating a cup for the candle. Before we do that, I just wanted to show you this candle holder. I was making it out of Virginia pine. I love the grain. I think the pine is the issue in this candle holder, but also I put the axes too far on the outside, so I didn't have a lot of wood to work with. Nope. And there you have it. Not every project is successful, but I certainly do learn from all of my mistakes. So here's the finishing cut on a project very similar to the one I was working on. This one is spalted holly. You can sort of see the dust coming out of it. The piece of wood I had on the lathe for the rest of this project was a beautiful piece of curly maple. But here I have it on the center axis, and I'm forming the top part, which will receive the cup. And here's the way I deal with the end. I've already drilled the hole. So I either use a wooden plug, or since then I've decided to make a jam chuck in my 4-jaw chuck. It's a little less wobbly than that plug is, in order to take the tenon off and create a flat bottom. So in closing, I hope that you see how many options there are, how to think about turning a multi-axis spindle, all the variations, all the sizes of wood. I think the sky is the limit, and the reason I like to teach this is to share with you all the variables, all the ways you can have fun with this type of turning. Thank you for your time.